Okay, so we're happy to have Mykola Dedushenko from Center and you the SCFT VOA correspondence.
Okay, thank you for inviting. So the subject that I chose to talk about is something that is probably known to some experts in the area, and certainly something I've myself thought about these ideas a long time ago, almost in grad school, but back then it never led anywhere. But then over the years, some other tools were developed, and so somehow I felt compelled to go back to this and revisit. So the motivation of the things I'm going to talk about is to unify and sometimes explain several things. So unify and explain a few things so on the one hand there is this VOA associated to 40 n equals to SCFTs, which is due to well-known work of Beem, and Lemos, Costello, Van Ries. Right, so nothing much to explain here. I think that their description is already pretty much optimal, but so here the unify applies. Because we'd like to connect it to a few other topics. One is the boundary VOA. Let me write it as BVOA, boundary VOA of 3D n equals 4 theories associated to a boundary condition, let's say B, of a 3D n equals 4 theory. Here, there's a construction of Costello-Gaiotto from several years ago. I don't remember which year there was, I think 18. Then there is also connection to the subject of vertex algebras in 2D 0,2 theories, right? So just as a reminder here, this UZ algebra is just like this. It has anti-holomorphic derivative on the right, and so Q cohomology turns out to be naturally holomorphic and has the structure of some VOA, which I refer to as chiral algebra of this two-dimensional theory. So now the tool that allows to connect these things is the omega deformation approach. To this SCFT VOA correspondence, which is sort of a reformulation of the original approach. And of course, it's, again, one of the things that was suspected from the very beginning as soon as the paper appeared 10 years ago. But the actual technical details were only worked out by Yagi O and also by Saibyok Zhang 4 years ago. And finally, another subject that I will relate to is some observation that we had a long time ago. Well, not so. No, I guess at the historical scale, just recently, in a paper with Gukov, Nakajima, And in that story, there was the Argyres-Douglas theory. Let's say, so Argyres-Douglas theory T, which was placed on S1 cross some 3 manifold. And this theory, it has global, let's say it has global symmetry Zn global symmetry. And in that story, there was a holonomy gamma, let's say it's 1 mod n. Holonomy on S1. Okay, in this, so basically 4D theory is reduced on S1 with a discrete holonomy, and it turned out that this thing was somehow connected to this resulting 3-dimensional theory was somehow connected to the VOA of the original 4D SCFT. So this is the part where I would like to sort of explain that connection using the a formalism that will lay down. So okay. So as I already mentioned, the idea will be to use the omega deformation approach to SCFT VOA and then build a certain story based on it. Okay. So so the starting point here is the holomorphic topological twist of a 4D n equals to SCFT, which is due to Kapustin in 2006. Let's consider our 4D theory on the, well, on a product of 2 surfaces. Let's say one is C, which I will also call sigma, and that will be, it will be thought of as a complex, so it's as a Riemann surface where the chiral algebra lives. And another one is R2, which will be thought, will be also, okay, I will also call it C. And eventually we'll also introduce omega deformation on this R2. Now in this 4D n equals, is this holomorphic topological twist, this plane is twisted, so by U1 little r, so every rotation is accompanied by the R symmetry transformation, and this plane, well, you have to do this, but you, if you want to consider more general Riemann surfaces, then it's twisted by U1R, which is the carton in the SU2R. So holomorphic topological means that this direction is topological, this direction is holomorphic. Okay, so here there's non-trivial dependence on complex structure. Deformations of Kähler structure are Q-exact. Here, deformations of metric are Q-exact. In particular, I could deform and consider replace this thing by everyone's favorite object, the cigar. Which I still call C. But it has to maintain the U1 isometry. And the supersymmetry is still preserved thanks to the U1 topological twist along this cigar. Now, when I have a, say, 40 n equals 2 on this sigma cross C, I can think of it, I can usually describe higher dimensional theory with certain amount of supersymmetry as a lower dimensional theory with infinitely many fields and half of the supersymmetry. In particular here, I can describe this 4D theory as a 2D n equals 2, 2 on C, but with infinitely many fields. So with infinitely many fields, right? And it's well known that you can only make half of the supersymmetry manifest because the full supersymmetry algebra involves translations in all 4 directions, and now you only want to have half of them. For example, if you have a gauge theory, in 4D with gauge group G, then in 2D you end up with gauge group, let me call it curly G, which is just maps from my sigma to G. So here one important point is that the HT twist, this 4D HT twist, is a B twist of this 2D 2, 2 description. Well, you can see it in many different ways. For example, one way is to say that, well, if I have what I have in 4D, I have SU2 cross U1 R symmetry. In particular, I have U1 R, capital R, and U1 little r. And if I decided to twist this 2D theory by U1 capital R, this one is actually, it's non-chiral, it's like not axial R symmetry. So this would lead to a model. Whereas U1 little r is the axial R symmetry, is the one that can have anomaly if you don't choose matter carefully. So this one, twisting by this one leads to the B model, and indeed on the C, and this 2D 2, 2 description is lives on the C. On this C, we twist by U1 little r. So, okay, so this is, by the way, Yagi O. In the case of Lagrangian theories, so if you have gauge theory, so 4D gauge theory with hypermultiplets in the representation R plus R dual, where R is a complex representation of G, then let me label variables in R as gamma and variables in R dual as beta, then this 2,2,2 description involves superpotential, which is integral over sigma of beta del bar gamma. Well, one can, if you look carefully, you'll see that because of this twist, beta gamma is actually a 1,0 form, and then this introduces 0,1 part, so it can be integrated over sigma. And A, the anti-holomorphic part of the gauge field along sigma, it's actually one of the chiral multiplets in this 0,2 description. So it's 2D 0,2 chiral, lives in the 2D 0,2 chiral multiplet. So overall, this 2D 0,2 description has a vector multiplet, 2D vector multiplet, in adjoint of this big gauge group G, curly G. Then there's AZ bar, which is 2D chiral multiplet in adjoint. And then you have gamma and beta, which are also 2D chiral multiplets. So just to give an example of how this two-dimensional description works, then one can check carefully that it actually reproduces the four-dimensional theory. Now, both A and B models in two dimensions, they admit natural omega deformation. Omega deformations that with let me just call it A epsilon, B epsilon. Now, if I chose to perform a twist along sigma, along C, this would lead to the story of.
Sorry. So the B twist is in the interior of C.
Yes. So if I chose to perform a twist, that would lead to the story of Nekrasov-Witten, which I won't talk about, but maybe I'll briefly mention something later again, where they engineer CC brain using this type of constructions. And the B twist, it leads to this chiral algebra or VOA construction. So just to maybe as a brief reminder, in two dimensions, the usual definitions, there's the A model supercharge is usually big as this one. The B model supercharge is this one. Both of them are nilpotent. However, they admit deformations where they are no longer nilpotent, but rather they square to a rotation, where V, well, it's just my Swan isometry of C. In flat space, This is not part of your Poincare algebra, because if you study Poincare supersymmetry, there are only translations there. There's no rotations. So this is not in Poincare. Susie? Right, so therefore it's a genuine deformation. Unless, so in flat space, in, let's say in R2, unless your theory is superconformal, SCFT, unless you have SCFT, then in this case, this deformation is equivalent by a change of variables, by field redefinition, to simply picking a superconformal supercharge. Let's say in the B case, some supercharge of the type Q plus S, okay, where you take sum of Poincare supercharges and superconformal supercharges. Because now in the superconformal algebra, of course, there are rotations, and you can find a supercharge that squares to the rotation. So so one can actually, the way to come up with such field redefinition is start with the omega deformed theory on the plane, then use conformal map to map it on the cylinder. Then on the cylinder, the rotation becomes a translation, and it's easy to identify the explicit field redefinition such that it removes the deformation. And then after that, since it's a CFT, you can map it back to flat space, to the plane, and then you just recover Q plus S. So there's a way to remove it. Now, in the omega background, the theory localizes to the tip of the cigar. Now, if I perform localization using supercharge QB, basically what I get in the B case. I think, I mean, if I'm in flat space, then 2D series is going to be just automatically a CFT. So if I perform localization by QB, then what one ends up with is basically this superpotential restricted to the origin of, so at the origin of C epsilon, it acts as a action of your two-dimensional theory, and you basically gauge beta gamma system in this way by localization. Which is, of course, what one gets in the four-dimensional VOA SCFT correspondence for Lagrangian theories. Here, there, the vertex algebra is just the gauged beta gamma system. Now, in non-Lagrangian theories, this is also supposed to work at some formal level. So I guess I shouldn't write on the stationary blackboard, right? Is that the convention?
Yeah, you can use this board.
You don't want it to be seen.
Yeah, if I use that board, then I wouldn't be seeing it. Right? I'll just erase, yeah. In general, if in non-Lagrangian theory, what I could say is that suppose you have T mu nu is the stress energy tensor of your four-dimensional theory. Let's say that there are indices I that correspond to sigma directions and indices A that correspond to C direction. And then I can define theta AB, which is T AB integrated over sigma. And well, one can check that this is now the conserved stress energy tensor in the two-dimensional description. And then when you perform the topological twist, this theta is replaced by theta tilde, which differs by some derivatives of the corresponding or symmetry current, which this two-dimensional R-symmetry current is also defined as the four-dimensional R-symmetry current for little r integrated over sigma. And then the whole idea of the twist is that this thing is Q-exact. In particular, in the presence of omega deformation, I'm only allowed to deform the metric in such a way that the isometry is not broken. So I guess I could fix the metric here on the cigar to be, maybe I'll write it here. If the metric on the cigar is the usual one, then these deformations correspond to deforming the phi-phi components of the metric, and in particular, the property that is a topological twist means that the corresponding phi-phi component of the stress energy tensor is Q-exact, which precisely means that I can perform this deformation sort of at this abstract level without specifying whether the theory is Lagrangian or not. So this construction should work in general. So let's say now I am on the cigar. So on the cigar. Here, there's a curved region, and here there's a flat region. So it's flat here. As I said previously, in the flat region, the omega deformation is trivial and can be undone by a field redefinition, whereas here, in the curved region, it's a non-trivial deformation. So this was used in particular by Nekrasov-Witten in the case of A twist. Now let's do it here in the B twist. One can look at this region, which looks like R cross S1. This is S1 parameterized by phi. And simply remove the omega deformation. After that, it looks like we just have our original SCFT, but reduced on the circle. However, this region will produce some natural boundary condition in this three-dimensional theory. So what I want to say is that I want to perform dimensional reduction on this circle, S1 phi, and describe the boundary condition that I get in a three-dimensional theory. So just as an aside, when one does this, performs this construction with the A-twist, as in the class of Witten, that was, you get this 3D theory, and then you can further reduce it on the circle to get certain 2D theory. And in that case, this thing engineers you the CC brane, the canonical quasitropic brane of the two-dimensional theory. And if you have a boundary at a finite distance here, then in this way, in the class of Witten, they ended up with a 2D theory on the strip. You have CC brane here, you have some Lagrangian brane here, and that's basically the brane quantization setup, and they used it to explain some connections between 4D n equals 2 and some other quantum integrable systems. But now here, and they had to sort of work, do some, anyways, they had to work to perform this field redefinition. Here, it actually is kind of, in the B case, it's a bit easier. I'm not going to write it down, but explicit change of variables allows, in the Lagrangian case, at least I can write it. So if I have a omega deformed action of this 2D B model, I can perform change of variables and obtain that it's actually just the undeformed action. And here I'm talking about the full cigar. It's undeformed action plus actually, right. Here is the superpotential. Well, I'm just writing it explicitly. And then after you integrate by parts, you see that this additional term only receives contribution from the region where the derivative of rho of r is non-zero. So basically, all you get is this additional deformation that's coming from this region after the change of variables. And in the 3D limit, if you take the 3D limit, this thing is basically, well, it's like proportional to epsilon and the radius of the circle, and then there's just the superpotential, or rather its conjugate evaluated at the tip of the cigar, which now becomes the boundary. Right. So that's the picture. So what we get is a boundary, some boundary condition deformed by this additional boundary term. What is the boundary condition that is, well, that's whatever you get at epsilon equal to 0. Well, because I integrate this by, so here, this is an integral over cigar, I can integrate it by parts.
I was thought that the contribution down there is, does this thing depend on the choice of row at all?
The choice of row? No. So if I integrate this by parts, I will get this. And so it only receives contribution from the region where this derivative is non-zero. And in the 3D limit, I could basically pull this out of the integral, the W bar evaluated at the tip, and then here just integrate. It's just rho squared at 0 and far away. So it doesn't depend on the shape, it's just that. And that's the R squared. Yeah, I picked that rho at infinity equal to R.
And the choice of what happens at infinity, is that an answer?
Well, I guess I assume that that W bar vanishes at infinity, which is the case in Lagrangian theories where W is just beta del gamma. So what is the boundary condition at epsilon equals to 0? Well, without omega deformation, I just have cigar with U1R twist. Nothing fancy. This HT twist works out in such a way that whereas on C we have 2,2 supersymmetry, on sigma we have 0,4 supersymmetry. So I guess I should add it as a remark that in HT twist you have 0,4 supersymmetry along sigma, and in particular it means that whatever this reduction does, it gives me some. So here I have my 3D n equals 4 theory that comes from the reduction, and here I get some 0,4 boundary condition. In particular, in Lagrangian theory, it's just this boundary condition is just Neumann for everything. For all bosonic fields. Basically, the reason is that the cigar doesn't constrain the boundary value of anything. Now, what we have is that we have this 0,4 boundary condition deformed by this boundary correction. What does it do? Well, I guess at this point I can already point out that this is precisely, in 3D, this is precisely the setup of Costello-Gaiotto, where they construct holomorphic boundary conditions in Rosansky-Witten twisted and mirror Rosansky-Witten twisted 3D n equals 4 theories by starting with 0,4 boundary conditions and deforming them in a certain way. Let me briefly review that. So I was told that there's no upper limit for, is that just?
We haven't had anybody really do that. They've always done it.
Okay, limit hasn't been tested yet, okay. Because I'm sort of taking my time. In some conventions, 0,4 boundary condition preserves supercharges, let's say Q plus bar, which is a 0,2 algebra, and another copy of 0,2 algebra, as well as Q plus prime, Q plus bar prime. On the other hand, the 2,2 boundary conditions, they preserve the same two supercharges Q plus and Q plus bar, and then there's also the opposite chirality supercharges Q minus bar. Now, in these conventions, the 3D A and B twist correspond to the A and B twist at the 2,2 boundary in the two-dimensional sense. Namely, if I choose the supercharge QA, which is Q plus bar plus Q minus, this is, it goes by many names. It's a 3D A twist, topological, because there's also another 3D A twist that's in the n equals 2 theories, which is not fully topological, it's partially topological. Here in 3D topological A twist, it also goes under the name H twist, or mirror to Rosansky-Witten twist, okay? And QB, which is 3D B twist, also called C twist, because in 3 dimensions you twist by the SU2C R symmetry, or it's the original Rosansky-Witten twist. So, as you can see, 2,2 boundary condition is compatible with both. So, compatible with both. In particular, this means that once you have a 2,2 boundary condition, it leads to a topological boundary condition in either Rosansky-Witten or mirror to Rosansky-Witten TQFT. So maybe I'll just call it either TQFT B or TQFT A. Now, Costello-Gaiotto asked how to construct holomorphic boundary conditions. Like one want to look at something like 0,4, but they're not compatible with these twists. So the answer was to deform them a little bit. To get something compatible with A, you deform 0,4 boundary condition a little bit to preserve, well, in general, you deform it to a 0,2 boundary condition. I guess you could also just start with 0,2, but then it's a little less clear, like how to describe it. You deform it to preserve the same Q plus, but then Q plus bar is deformed to the A-twist supercharge. Or I could actually put a coefficient here, because different values of epsilon, as long as they're non-zero, they're all equivalent anyways. And this is like the deformation parameter. And if you want to be compatible with B, then deform your 0,4 boundary condition to preserve, again, Q plus and the B model supercharge. Now there's a, I mean, this thing is a rich subject on its own. You can just start studying such holomorphic boundary conditions. Oh yeah, and this is clearly a holomorphic boundary condition now, because let's say in this example QA, if you anti-commute it with Q plus, what you get is anti-holomorphic derivative on the right. So clearly now at the level of QA cohomology, this boundary condition is holomorphic. There's some boundary vertex algebra, and it's an interesting subject on its own. Now, we're interested in the very particular case, in the application to 4D. And a slightly confusing detail here is that even though I was considering B twist on C in this two-dimensional description, now in terms of the 3D bulk theory, it's actually the A twist. Which, I mean, if you think about it for a little bit, it's not that crazy, but maybe just point out that from the point of view of 3D, it's the A twist that comes from the chiral algebra construction. So just to remind you, we have sigma cross C with omega background. It's here on B, it's an omega deformed B model. And here it's actually A twist. I mean, because in the HT twist, you twist by SU2R, so here it's A twist. And that eventually, after reduction to 3D, leads to this A twist. Now, what is this deformation? So deformation, how does it work? So you have a boundary condition, which is 0,4. So it preserves this 4 supercharges. And what you want to find an operator, O, such that it commutes with Q plus and Q minus. So Q minus is not among preserved supercharges, it's something that's preserved on the 2,2 boundary. But it doesn't commute with Q plus bar. Rather, the commutator gives you a particular component of the supercurrent, the normal component along the boundary, the normal component of the supercurrent, where this is a current for the supercharged Q minus. Once you find such operator, all that you have to do is actually use it as a boundary deformation. So you insert it along the boundary. So this is our boundary R2, and then epsilon parameter appears here. You see, because this O commutes with Q plus, this deformation, well, it preserves Q plus, doesn't do anything to Q plus, but because it doesn't commute with Q bar minus, it actually breaks it, or rather, if you look more carefully, it deforms it. So now the Q bar plus is broken, but instead a combination of Q bar plus and Q minus. And now deforms q bar, deforms, well, with this sign, it's actually q bar plus minus epsilon q minus that is preserved. So we end up with a boundary condition with such deformation boundary condition that preserves these two supercharges. And it really seems to be an optimal way to describe it, because like you could try to run this procedure in Lagrangian theory, say for the free hypermultiplet, and you know that insertion of some boundary terms can be like, you can perform your variational problem in the presence of this boundary term and observe that it deforms your boundary condition. But that explicit deformation of the boundary condition for free hyper, it actually violates the reality condition. So it's like you have certain reality condition in the path integral, like you integrate over the middle dimensional cycle in the complexified space of fields, but then this reality condition violates precisely at the boundary. If you try to sort of remove this deformation and instead deform the like classical boundary condition. So it's a little unclear how to do that, but in quantum theory it makes sense. Just describe it in this way. You start with some sensible classical boundary condition and also include boundary interaction of this form. And it works. Now, what is such O? Well, since the supersymmetry connects O to the supersymmetry current, then there's a canonical way to find such operators. Use the stress energy tensor multiplet. So the supersymmetric field theories, the Lorentz invariant ones, they always, well, at least they have the stress energy tensor, which is part of some multiplet, and you can identify what operator in that multiplet does the job. And actually, it turns out that it's just a component of the arc symmetry current. So I'll just write it here in this green box. This O is, you can take the SU2H arc symmetry current. So this refers to the SU2H arc symmetry. So it's the 3D n equals 4 arc symmetry that rotates the complex structures of the Higgs branch. And you take, it's like the certain, it has SU2 indices, you take component minus minus. In these conventions, I will remind you that in the 4D construction, the plus plus component is the Schur operator that corresponds to the stress energy tensor in the chiral algebra. This is the corresponds to the stress energy tensor in the VOA. So this is related to that operator. So there's a canonical choice, sort of such operator, and indeed, in Lagrangian. Okay, I'll just write here once. In Lagrangian example where we had, we call the W was beta del bar gamma, so W bar is just, is this, let's say for a free hypermultiplet. And this is actually nothing else but the component of this arc symmetry current that I'm talking about. So there is a good choice of the boundary deformation. Okay, so what is the lesson here so far? And the lesson is kind of simple, is that using this omega deformation approach to the SCFT VOA correspondence and reduction of the cigar, we see that omega deformation in 4 dimensions produces this deformation of the boundary condition that Costello-Gaiotto used to define holomorphic boundary conditions in the topologically twisted theory. Now let me describe an application of this to explain that connection to MTC and TQFT and stuff like that. Anyone watching this in headphones together?
Yeah.
Rapture their eardrums.
They click to sell at a tab and then.
Oh, is it actually online right now? Suppose I have. So I'll come back to Lagrangian theories a bit later, unless I will be stopped from doing so. But let's now consider a non-Lagrangian, say, Argyres-Douglas theory of some. For example, it could be something known as A1, A2, or H0 theory. Such theories, they typically have, so it has some Zn global symmetry. Which is related to the fact that the R charges are fractional. So U1 R charges of various multiplets are fractional, are the form n over n, and so capital N is their common denominator, and that's the n that appears here. And also in the class S construction of such theories, you have well, you consider your 6D theory on the reduced on CP1 with wild puncture and possibly regular puncture on the other end. And so you study Hitchin system on this CP1, try to perform quasi-classical analysis. You find that there are Stokes rays, and there are precisely n of them. So that's this n that controls this global symmetry. But from the point of view of 4D field theory, you could just say that this is because the R charges are fractional.
Is it one puncture? Repeat again what the puncture?
So it's a CP1 with wild puncture, and then say on the north pole, and then on the south pole you may or may not add a regular puncture. That's like this construction of generalized Argyres-Douglas theories. Now, why does this? Why do fractional R charges imply presence of this global symmetry? Well, because you have your U1 R symmetry, but then as you perform a 2π rotation, which is a trivial transformation from the point of view of supersymmetry algebra, you find that some operators pick up a phase. Therefore, there is a such extension happening by this Zn, right? Where this is an n-sheeted covering. And this is the Zn I'm talking about. So in other words, the 1 mod n element in this Zn corresponds to e to the 2 pi I rotation in U1R, which is a trivial rotation, but then now what happens if we perform this construction of reduction on the cigar with a twist for such a theory? And by the way, in this example, it's a Z5. That's the global symmetry of this theory. Well, it's a certain class of 4-dimensional n equals 2 superconformal field theories that don't admit n equals 2 Lagrangian description. By now, people have come up with n equals 1 Lagrangians that flow to such theories, but they were discovered originally at the special singular loci of Coulomb branches of larger Lagrangian theories. Let's say you start with SU3. Cyberquin theory, like just Supreme Mills, consider the codimension to a singular locus on the Coulomb branch, and then there were arguments using the Cyberquin theory. People come up with some way to show that there is this special superconformal theory that lives there, which has sort of mutually non-local degrees of freedom that would be impossible in a Lagrangian theory. So, in the 4D n equals 2 Lagrangian. They also have non-class S construction where you start with 6Z2,0 theory, reduce it on the sphere with wild puncture. Okay. So again, here's the cigar. And here we have, because of the topological twist, remember there's a U1 topological twist, in the curved region, there is a flux. Here we have a flux of U1R symmetry. What does it mean? Well, it means that I literally turn on the curvature for this U1R symmetry and have a unit flux here. Here I'm using conventions in which the charge of some supercharge will be plus minus 1/2. Then I turn on the unit flux here, and which is the equivalent to topological twist. Now, because I have this flux here, I get a holonomy. I automatically get a U1R holonomy. Well, one which is e to the 2 pi I. Okay. Precisely what I need for this Zn to get activated. In Lagrangian theories, all this does, what does it do, this holonomy? In Lagrangian theories, like if I didn't have a topological twist, so without topological twist, so this circle, which recall I called it S1 phi, S1 phi would have Navier-Schwarz spin structure, okay? So the anti-periodic. Now, with topological twist, or rather this, because of this U1R holonomy, it changes periodicity for fields that have half integer R. So basically, it ensures that now S1 phi has an Raman spin structure, which is precisely like it's like how it was in, say, TT star geometry of Chikoti-Waffe, no? You know? Where the presence of topological twist changes the spin structure. But now, because in the Argyres-Douglas theory, this full circle rotation of the R symmetry, it's a non-trivial Zn holonomy, we get this Zn holonomy for free. So in Argyres-Douglas theory, we get this 1 mod n holonomy along S1 phi for free. So in other words, the reduction that you get from 4D to 3D is not the usual supersymmetric S1 reduction, but rather it's a twisted reduction in the presence of this holonomy. Which, by the way, hasn't been studied in the literature in this particular case. Of course, such reductions appear in various other contexts, like when 6D theory, when you reduce it to 5D, you like do twists by auto-automorphisms to get non-simply laced algebras and stuff like that. But for Argyres-Douglas theories, people have studied the three-dimensional reductions without the Zn twist. And so there's a known language how to write 3D mirror theories, 3D mirror duals, and so on. But in the presence of this twist, it's not known. Also, what in a lot of these examples, what this I'm not confident enough to say that in all examples, but at least in a large family of examples, this Zn twist removes Coulomb branch. Actually, maybe in all of them, at least in those that originate from the class S construction. Instead, you replace your Coulomb branch. Let's say so your Coulomb branch is replaced by some fixed locus of the Zn, which turns out to coincide with a fixed locus with respect to U1R, and so it's just some collection of points. So the A twist here is, in some sense, should be good. The 3D A twist, which is the H twist, it's the one that typically gives you something like a sigma model into the Coulomb branch. It gives you some, well, in some sense good, or like something like, looks like a sensible TQFT. And for sure it does when there's no Higgs branch. So if 4D theory T has no Higgs branch, like a good family of examples is like this A1, A2, or A1, A2n. Like this is a family of examples in which the corresponding vertex algebra is just Virasoro at the level corresponding to some non-unitary minimal models. Then in this case, after the reduction, the 3D n equals, so n equals 4 theory, it also has no Higgs branch, and also, as I said, the Coulomb branch gets removed. So 3D n equals 4 has neither Higgs branch nor Coulomb branch. So no Higgs branch and Coulomb branch. Such theories have started to appear in the literature recently, and they're usually such 3D n equals 4 SCFTs are usually referred to as rank 0. 3D n equals 4 SCFT. Now, not to confuse with rank 0 in 4 dimensions, where it refers just to the complex dimension of the Coulomb branch. In 3D n equals 4, the terminology is that rank 0 means that Higgs and Coulomb branches are both 0-dimensional.
We often study math theory. We often study math theory, even when they do have Higgs and Coulomb branches.
What's different is that it's a genuine interacting SCFT. It's not a massive theory. It's like it has some massless degrees of freedom. So of course you could consider massive theory, and then you say that TQFT, and TQFT is of course a very special example of SCFT.
Even that, I mean, are there some genuine new phenomena that wouldn't have happened in these masked up ordinary 3D and 4 theory?
Well, yeah. First of all, these are non-trivial SCFTs. So they have some spectrum of operators, OPE, and stuff like that. So it's not just TQFT. Then they cannot be described using 3D n equals 4 Lagrangians, because such Lagrangians always have either Higgs branch or Coulomb branch. There's some papers by Gang and Yamazaki and Kim and others where they come up with 3D n equals 2 Lagrangians that float or conjecture to flow to such rank 0 SCFTs. So seem to be pretty interesting objects. And in particular, in such SCFT, you can perform topological twist, and you get some healthy TQFT. It happens to be non-unitary TQFT, but otherwise it's pretty healthy. And so some TQFT3 that follows from the, let's say, in our case, from a twist. In some sense, well, states in this TQFT are going to be labeled by these fixed points on the Higgs and Coulomb branches. So what we get here is that this construction with a cigar gives us a homomorphic boundary condition, and here it is this rank 0 SCFT, or its topologically twisted version, say TQFT 3. Boundary condition, let's say, call it B, and then the boundary chiral algebra, so this boundary VOA associated to this B happens to be the VOA of your parent 4D SCFT T. well, that's by construction, because that's how we define this boundary condition, such that it carries this VOA. Now, this TQFT has some line operators, some lines, and then the category is this MTC, the modular tensor category that underlies the TQFT3. But now lines, they also give you modules for the boundary VOA. Lines, they engineer modules for VOA of this, the boundary VOA. So what it means is that for any such holomorphic boundary condition, you naturally get a functor from the category of lines to the category of modules. And well, there may be multiple holomorphic boundary conditions, but one natural hope, and perhaps conjecture, is that this particular boundary condition that follows from this construction, so this natural boundary condition, gives you actually the equivalence. And certainly in good examples like this, you observe that this is true. And that's exactly that observation from 5 or 6 years ago in the paper with Gukov and Nakajima and others, where we observed that you start with the Argyres-Douglas theory on the circle with the ZN twist, the ZN holonomy. You perform topological twists of the 3D theory, you get some TQFT, you compute partition functions, identify MTC, and it is the category of appropriate modules for this boundary VOA. It's kind of emerges here, well, at least the functor emerges automatically, that for each, from MTC to the category of modules. And it's like one can conjecture that for this natural boundary condition, it's actually equivalence. Then the standard story is that the choice of state in the TQFT3.
So the boundary chiral in this case is what? You said it's something known, the minimal model?
Yeah. Like in this case, it's the minimal models.
Which specific, so?
What is it? 2n plus 3. They are non-unitary minimal models.
And corresponding to
it's this n. So in particular, for A1, A2, you have 2, 5, which has like central charge. Yeah.
And so it's the statement that the 3D theory will give you only the chiral vertex operators that actually correspond to the line operators will be just those that make sense in theory and none others. You can actually stand from the top too. I mean, is this, do you get this theory on the nose or is it some approximate thing?
This?
Yeah.
Well, it follows from the construction that, because you start with something that gives you VOA of the 4D theory, where it has been identified before.
And the identification comes from what? How can you identify it so precisely?
Well,
They're characters, and these VOAs have to be simple. So you can set up basically an injective map between sort of fugitives or operators and operators in this little model, because it's simple and you use characters, that's the rest. I think that's what portrait is.
So
Yeah.
it's, this VOA is the one that of Beem, right?
Yeah, there's a lot of like it's literature on this subject where people use various tricks, like indeed computing characters, and you can identify central charge immediately once you know the 4D SCFT. Some other constraints. So it's like technically all these statements are conjectures, most of them, but they're like established with high confidence.
And in particular, you can replace this. You can make sigma an arbitrary geometry surface, and you get
Yes, that's not something that's like obvious from the 4D, the original 4D construction, but once you formulate it in this way, indeed you can take arbitrary Riemann surface, and then this 3D picture tells you, so okay, so here let's say you have arbitrary Riemann surface, sigma, and then 3D TQFT gives you, you pick some state in the Hilbert space associated to this sigma in the TQFT, and it gives you conformal block for this VOA associated to sigma, and the choice of the state gives you some conformal block.
Do you have ways of engineering the agency conformal block?
Well, I mean,
Like in science theory, we do have such things,
right. Once you identify the TQFT, you could literally try to pick some state. It's a finite dimensional space. You choose some state, and
I know formally, yes, but I guess I'm asking how much of this do you understand microscopically studying from 2-0 theory?
6Z to 0 theory?
Yeah.
I'm not sure. I don't think about it in terms of 6Z to 0 on a daily basis. So like, but yeah, perhaps there is something to be said there. I'm not sure. Okay, so and as I said here in this story, there is an interesting open direction is actually identifying this 3D theories that follow by the twisted reduction, ZN twisted reduction of 4D Argyres-Douglas theories. Presumably that's a source of, like in particular, if you start from this and perform such reduction, you'll get a family of rank 0 theories in 3D. And there are already some known families of rank 0 theories, but if they match, what's the mapping? It's not known. Now let me finish with another topic quickly. Unless.
And we could have run this story with an arbitrary process theory.
Yes. Yes. Now I want to connect to. There was one more blob in that diagram at the beginning was the 2D n equals 0,2 theories. So how do I do that? Well, instead of starting theory in the half space, I'm going to put it on the interval. Here I have my deformed 0,4 boundary condition, the holomorphic one. And on the other end, I'm going to put 2,2 boundary condition. So the topological boundary condition. So it's a 3D theory on the slab. You can think of it again in these terms that in the TQFT I have the holomorphic boundary condition, here a TQFT, and then here I get a state which is like corresponds to the boundary state of this topological boundary condition. So essentially, by choosing the boundary condition, it's like I'm choosing some conformal block for this VOA. Now I guess I'll.
Everything for you came from that boundary. What's the argument that it would get a conformal block for any VOA that changes boundary? There's no kind of separation of.
Sorry, what do you mean?
The entire theory is localized to the boundary.
Yes.
So how do you see the changing boundary conditions to a different?
Well, I'm not changing this boundary. I'm not changing this boundary condition.
You're doing the other.
Yeah. This one gives me a state. Huh? Well, it's going to be the same 2 dimensions where the VOA lives. Yeah.
So your VOA lives on the left boundary?
Yes.
And again, not apparent to me. Maybe I'm not thinking about it the right way. Well, why is it then that choosing the right boundary gives you a common block that you? How does it feel?
I mean, so, okay, so do you agree that picking a state in the TQFT gives me a conformal block?
Sure.
Now I can imagine that I have a boundary condition. It generates me a certain boundary state, which is of course not in the Hilbert space, but then after a short Euclidean evolution, it becomes a certain state in the Hilbert space. It is supersymmetric, and it is cohomologous to some vacuum.
It's not apparent that all of these methods is that cool. If I cut this thing anywhere, I get it. Because your arguments very much relied on very special properties that happen at the tip.
No, but that's what determines the holomorphic boundary and the chiral algebra, and that's totally fine. I'm not changing that.
Okay, so but I guess you'll tell me that you have full 3D quadratic covariance development.
I do have that if I perform twist, yes. So at the level of Q cohomology, indeed, there is. I could also say that, okay, so what does it mean that I have a holomorphic block? It means that I can start computing correlation functions of some local, I can start inserting local operators that belong to the chiral algebra along this boundary, and then just computing partition function with such operators inserted. And The answer is going to depend on what boundary condition I choose on the other end. There might be some more subtleties with it, because boundary is not exactly the same as the vacuum state, because it also carries some boundary anomalies. So, but
I think your second argument should be more or less fine. If you put some operators on the left guy, and then by a topological invariance, you can bring the right guy arbitrarily close, and you can reduce to some conformal block calculation determined by the other guy.
okay. So if I have just a 0,4 on the left and 2,2 on the right, then the Commons use it as preserved is 0,2, of course. Now, if I have deformed (0,4 on the left, which I introduced before, and I have 2,2 on the right, then let me use this loose notation. What I get is this supersymmetry where I have these two supercharges preserved, Q plus and Q plus bar plus epsilon Q minus. But these two, they still form 0,2. It's just slightly deformed because the second supercharge is deformed, but it's still 0,2 supersymmetry. So in other words, the effective description is with these two boundaries present is still some 0,2 model. Well, the holomorphic twist, like in this holomorphic direction, means that I study cohomology of this supercharge in 2D 0,2 theory. So in other words, such interval reduction produces some effective.
Let me ask you, sorry, would you know how to make it concrete? Like, these minimal models have like the field representation. Would you actually know how to pick a 2D boundary condition that ticks out from one block?
I only know how to do the non-Lagrangian examples. It's so non-Lagrangian, like there's something to.
But free field representations, they usually come from the keeping the theory, and you don't need a Lagrangian description of free field representation.
I mean.
So have people tried to actually spell this out?
Sorry, spell out what?
Well,
like people come up with free field representations of these algebras. But in this story, this is not like to make this concrete in the cases of Argyres-Douglas theories is something that I cannot do because maybe okay, I don't have time to come back to this, so let's say now. As I said, the
maybe I can ask you this, like, if we didn't take the circular reduction, right, you would do not very not work. If we didn't take the circular reduction, okay, and here I will ask you, what are we learning here about? Like, are we learning something? Is it an exercise in understanding understanding gauge theories and what new insights should we take from them? Does it give us new muscle somewhere? It should, right? Say, if we didn't do the circular reduction, do you get categorification of these structures? So there arises the grading matrices, there arises indices. So we get a new calculation that we didn't have before.
I'm sure we do. Well, all this, I can make it very concrete in the, again, Lagrangian examples. Which I was about to get to, but actually, I wish to make it concrete in non-Lagrangian examples too. That's something I'm kind of thinking of. But and then in the end, it would give you a 2D 0,2 theory whose chiral algebra has something to do with the VOA of the original 4D theory, which is pretty interesting. It sort of gives you a way to produce free field realizations because right now they are, it's a bit of a guesswork, and like the way they write them. I mean, I don't know if you agree with no.
Yeah.
Yeah, you just have a free field realization. Does it mean something? Like, why is it such a thing?
Well, because once you have a 0,2 description, you could say that in some sense you get chiral differential operators on the target, plus something happening at singular loci, which is already in the spirit, the free field realization. I don't know if you agree with
to an extent, I mean, I think that the difficulties are in sort of the formal localization theory of chiral differential operators as like a sheaf over the Higgs branch. That's like the hard thing.
Yeah. Well, it's certainly not going to be over the Higgs branch here. It's going to be some complex Lagrangian submanifold of the Higgs branch where the sheaf lives. Which is, by the way, well.
So what is the singular?
Yeah, you can imagine having, like your Higgs branch is some kind of cone, and then the complex Lagrangian submanifold passes through the origin of that cone. But yeah, so the lesson here is that there is a certain effective 2D 0,2 description, which let me call it TB epsilon, which depends on the, so this boundary condition is canonical, this one, let's call it B. And it turns out that often, if not always, once you reduce on the interval, it washes away the omega deformation. So this 0,2 theory is the same one that you get here, which is, at least it's true in Lagrangian examples, and it's certainly convenient because it simplifies a lot of things. It's basically the presence of the second boundary makes this boundary deformation like irrelevant. It disappears. And then the VOA, so the chiral algebra of this 2D theory, with epsilon or without epsilon, you can think of this one as actually extension of the original VOA 4D by modules. So what I mean is that we have our VOA 4D living at the boundary here. So then we have topological boundary condition here. And if this configuration admits line operators that connect the two boundaries, which are modules for this VOA, then in the 2D limit they become local operators that may or may not extend the original 4D VOA. If this can be made thoroughly concrete in the Lagrangian example, so if we have G gauge theory with hypers in R plus R bar, well, let me just choose this boundary condition in the following way. So vector multiplet is given 2,2 Neumann boundary conditions, and then chirals in R, valued in R, given 0,2 Neumann, and in R bar 0,2 Dirichlet. Together, this is of course 2,2 boundary condition of the hypermultiplets. Which is, well, it's like I chose the complex Lagrangian submanifold, which is R in this case. And then as a result, I get to the n equals 0,2 theory, which is very simple. It's a G gauge theory with chirals valued in R. So it's a two-dimensional 0,2 theory. The cancellation of its gauge anomaly is equivalent to vanishing of beta function in the original four-dimensional theory. And then one can check that in this theory, one can compute VOA, actually the perturbative VOA. And let me call this theory something, what should I call it? I don't know. There's no other letters but T, so it's going to be T of G and R. And then the perturbative VOA of this theory, T of GR, is just Biarritz reduction of the beta gamma system, or like of this R value, or maybe I should write R plus R bar valued symplectic bosons. So you can actually just compute the perturbative vertex algebra in this gauge theory, and find that it's this. Now, this is precisely what's known to be the VOA of the corresponding SCFT in 4 dimensions, this Lagrangian theory. Now, here a sort of, now, of course I said perturbative VOA. a sort of speculation is that non-perturbative corrections, they correspond to instantons in this two-dimensional gauge theory, which are vortices. But in the three-dimensional language, vortices, they're actually vortex lines. So they don't live just at the boundary, they extend into the bulk. Therefore, these non-perturbative corrections, they're not associated with a boundary VOA, but they're something that become important in the 2D limit. So just dropping non-perturbative corrections in this example corresponds to looking just at the boundary VOA. And indeed, this gives the correct answer. So in this Lagrangian example, the dictionary is that perturbative VOA of this 2D 0,2 theory is the VOA of the parent 4D SCFT. Perhaps I should remind that in two-dimensional 0,2 theories, there is this like when you study sigma models, it is known that perturbative VOA gives you chiral differential operators on the target, and then non-perturbative VOA in general sigma models can be something completely different, can be zero, often.
So what's that statement? The non-perturbative VOA is
That it was it can be it often can be zero. Well, probably not here. So that's something that happens. This vanishing, it happens in 0,2 sigma models into targets like CP1, or like whenever you find a CP1 in the target. Here, my guess, or like conjecture, is that it can be trivialized because the non-perturbative corrections seem to be, what they're doing seems to be just the extension by these lines. Of course, it's an interesting but a sort of trivial example of Lagrangian theories, though it already leads to some interesting observations about perhaps free fuel realizations, especially if you consider example of SU2 with 4 flavors. In this case, the corresponding two-dimensional theory, it has a dual description as a Landau-Ginzburg model. It was studied 6 years ago in my paper with Gukov, another paper with Gukov. It has Fermi multiplet psi, which is just one Fermi multiplet, and then it has a matrix of chiral multiplets Mij, which is a 4x4 antisymmetric matrix. So Ij run from 1 to 4. So Fermi multiplet, chiral multiplet, and there's a superpotential J, which is Pfaffian of M. In this case, one can actually compute chiral algebra both from the Landau-Ginzburg side and from the gauge theory side to find that it's the perturbative chiral algebra is SO8 at level -2, which also happens to be of course, the VOA of the 4-dimensional theory. But like you see, this Landau-Ginzburg description gives you an alternative realization of this algebra as something on this cone. One of the missing things, an interesting direction that I've also been thinking about is, instead of doing this reduction in 2 steps, where you first reduce on S1, get boundary, and then put on the interval, you could just reduce on the finite cigar right away. Or in other words, consider theory on sigma cross disk with some boundary condition along the boundary of the disk, and perform this reduction, and perhaps start with 40 n equals 1 Lagrangians that flow to Argyres-Douglas theories, put them on such background, and try to identify the 2D 0,2 theory that originates from the Argyres-Douglas. Well, here the challenge is to write a good boundary condition at the boundary of this D2 somehow. But, well, I guess that's all I wanted to say, really. Yeah, so here I guess the interesting lesson is, to me, is just connecting these different perspectives, different subjects, and also being able to write down certain 2-dimensional 0,2 theories that are related, whose chiral algebra is either the same or an extension of the 4-dimensional chiral algebra. Oh, and of course, characters. Well, anyways, I don't really know. That's it.
So I had a question. I think I already asked this, but I'm going to insist. So maybe in the case of SOA at level -2, do you have some expectations of which modules you should extend by? Or maybe in any like easy example.
Yeah, so well, first of all, if I could choose, first of all, I could choose different boundary conditions here on the right-hand side, and then I would just, perturbative algebra would enlarge, because I could have, let's say, some kind of Wilson lines that make sense, perturbative, it's like non-perturbative corrections, and they would extend the algebra, and that's easy to see. But then the non-trivial part is when I somehow picked the right boundary condition, like here, such that the perturbative chiral algebra is already the 40 VOA. Now the question is non-perturbative corrections. It seems like in this example, it seems like there's only one, perhaps line of one module that, because in this duality, when I said that this Landau-Ginzburg model reproduces SOA at level -2, I slightly lied, because there's additional thing, which is psi itself, which looks like a module for SOA at level -2. Now, people have, by people, I mean, there was a paper by Richard Igor, Eric Sharp, and perhaps Lockhart. Guglielmo, I think, yeah, it's 3 of them. They looked at the elliptic genus of this model, either from the Landau-Ginzburg side or from the gauge theory side, or they computed in gauge theory, and it decomposes into characters of vacuum module +1, non-trivial, non-vacuum module. And it seems that it corresponds to this psi. Now, it means that on the gauge theory side, there should be a non-trivial vortex, just one, that contributes that additional module, in addition to the vacuum module. Because from the point of view of this picture, of course, on the boundary you have only the vacuum module, and then everything else comes from the these line operators. It's at least for me, I don't know how many people are interested in this, but at least for me, it's a long-standing problem to how to understand this non-perturbative corrections. So which vortices you need to pick in the 2D gauge theory, and how they affect the chiral algebra.
I also have another question. So regarding this perspective on free field realizations, what sort of class of VOAs do you have this? Like, I guess what sort of class of 2D integral 0,2 do you have this alternative Landau description?
Oh.
Is it like only very specific cases?
I only know one case. This.
How did you obtain the Landau description?
From Seiberg duality in 4D n equals 1 theory. So we started from Seiberg duality, particular example in 4D n equals 1, the degenerate one where one of the sides is, it's not gauge theory, but just Landau-Gizmo model. Reduced it on a sphere and obtained this pair in 2D, which would yeah. But even looking just from the gauge theory perspective, you could say that at low energies, you're going to get some nonlinear sigma model with a singular target and some sort of perhaps additional degrees of freedom living at singularities. At some point, there was a hope that maybe this can be made more explicit and precise. For sure, the target of this NLSM is just the Kähler quotient of R, and it can be identified as the holomorphic Lagrangian in the hyper-Kähler quotient of R plus R bar. So. Any more?